Hello, this is Math 280 Multivariable Calculus. I'm Professor Wheatley. Our topic today will be vector fields and integration over vector fields. Okay, so what is a vector field? Definition: a two-dimensional 2D vector field, F, and this is, so it's two-dimensional, so it's defined on subset of R2, subset D of R2. It's a function, and it assigns to each point in D a two-dimensional vector, f of x, y. So a vector field itself is a function from R2 into the set of all two-dimensional vectors. So in other words, a point maps to a vector as opposed to what we're sort of used to when we have a function of two variables. Usually we have two inputs, so a point in R2 goes to a point in R. In other words, there's two input values and one output. That's a usual 3D function. This is different. This is a one point goes to, or one 2D point goes to one 2D vector, so to speak. So one viewpoint of this that is realistic is something like fluid flows. So you have some pipe, say, for example, and this is in 3D. I'm working, this is 2D, but if I alter things, I can simply replace all the 2's with 3's up here. I could replace 3D and to each x, y, z in D, a 2D or a 3D vector f of x, y, z. So vector fields are analogous in higher dimensions. The definition is completely unchanged. So suppose you're in some pipe and there's fluid flowing through it. Then at every point in that pipe, you can assign a velocity. In other words, depending on how the pipe is moving and the inclination of it and whether or not there is obstructions there or things that are slowing down the fluid flow, changing its direction, something like this, you could assign a velocity to every point in the pipe, and that would be a 3D vector field called a velocity field. So for example, as the pipe snakes its way through things, it's an indoor plumbing pipe. As it snakes around, goes like this and things of that nature, the velocity changes. It changes its speed, changes direction. At every point in the pipe, the fluid has some velocity associated with it. Okay, so that's a velocity field. How do we draw one of these guys? Well, when we have a usual function of two variables and one output, we have something in 3D. Here we're still in the plane. What we can do is we can take each point and draw along with it a vector. So how do I represent drawing a vector field? Drawing vector field. So we can't obviously draw every point. That's not going to happen. Otherwise, we'd just have a blob. Everything would be black because vectors would cover everything, in D at least. So let's choose some points in D, some representative points. Depending on the vector field, there may be points that are better choices than others. Some may be sort of strange depending on what happens. And we will draw f of x, y. That is to say, the vector from that point to its terminal point. So it's a vector with initial point x, y. So we choose some sample points in D, and we're going to draw a vector from those points to the terminal points. So as an example, let me get rid of this. We will put up here a simple little example. And 3D fields, draw them the same way. It's a little tougher to draw a 3D vector and have it look really accurate sometimes. So here's your field. Let's call it negative yi plus xj. There's a sample field, right? So in other words, when I plug in a point x and y, I get out an I and j component. I get out a vector. All right, so first of all, it's important to note this field has domain all of R2. In other words, every point in R2 has a corresponding vector. defined on all of R2. Vector fields are functions. They have domains just like any other function. So this is all of R2. Let's get some sample points here. So I'm going to pick some points that are reasonably random. If I plug in 0, 0, I get 0i plus 0j. That's just a 0 vector. So, and the 0 vector is the lone vector without length or direction. It's a point, so I mean, can't really draw this on there. It's not interesting, really. Let's pick some more interesting ones. Maybe we pick 1, 0. If I pick 1, 0, what do I get? Well, I get negative 0i plus 1j. So this guy is just the vector j. So let me maybe start drawing my field over here. So here's, well, let me make it bigger. Let's really try to get this to look reasonably good. So that's better. So I'm at the point 0, 0. That's just a point. That's not very interesting. I go to 1, 0. Maybe I'm there. I have a vector that's vector j. So now my vector extends up, say, like that. So maybe that's 1 there, right? So there is 1, 0. And let's see here. What else can we do? How about minus 1, minus 1? If I get that, I get a minus 1i, which is just I, a minus j. So this is I minus j. So if I start down here, let's see here, maybe I'm starting there. There's the point minus 1, 1. And the vector from it is I minus j, right? So you're sort of going, so your length here is root 2, right? And you're heading in a southeasterly direction. So maybe you're sort of heading down like that, right? And that looks a little far. We shouldn't mince words too much, but at the same time, we want this to look reasonably accurate. So maybe head down like there. There you go. The same place it was before. So this is clearly the point minus 2, 0, right? Because this would form a 1, 1 root 2 triangle, right? So there's your vector there. That's f of negative 1, 1. And what else can I do? F of 1, 1, sure. F of 1, 1 is minus I plus j. So here you are there, right? This guy, again, has root 2 length. He's going in a northwesterly direction, so maybe you're looking something like, well, that looks all right, I guess. So something like that, right? So there you are. There's your vector there. And in fact, you could sort of see, if you drew some more of these guys, what you would wind up with if you took the point. So here you're at 0, 2. If you took that point, you would wind up with minus 2i. So you would have a guy that looks like that, right? So that's now minus 2. And then if you kept going here, this is now what, minus 2, 2. So this would be minus 2i minus 2j, right, which has length root 8. So now you've got somebody who's heading down like this, and he's going to collide with the x-axis down there. And then you can also see that, I mean, you could do some other points. I mean, you could check these out, confirm on your own, but you've got some rotational symmetry going on here. In other words, this guy sort of forms a whirlpool effect. In other words, it's sort of tighter around here and not as tight as we go further out. And that one is there, and then you'd be shooting sort of down, be coming sort of down here like that, right? And this is actually going to be like that. At negative, what is that, negative 1, 0, what happens there? At negative 1, 0, you wind up at, yeah, there. How do you get over there, though? Yeah, so it sort of looks like this, yeah. And you could check this out yourself. You got some rotational symmetry going on, so you have some points that wind up looking something like this, and then another point comes out here, and that's 2. And so you can see this is kind of having a little bit of a spiral effect here, and it'll go up, and let's see, this is what, 2, 0, so it's going to go up 2j, so it'll go up here like that, and then it'll spiral around. So you can see this is kind of a whirlpool effect. But certainly you can draw as many vectors as you need to make it apparent what's happening here. This is just a few things in what we have here. Okay, and certainly this thing is going to spiral bigger and bigger as it goes out, because the larger your x's and y's are, the longer the vectors will be, and the more they'll spiral out. Okay, component functions. Let me get rid of this here. We can talk about that. Well, let me say one more thing about it. We can see that both the I and the j components are functions of x and y. Happen to be just y here and x here, but they could have been both x's and y's included in both of those pieces. So those are called the component functions, just like the components of a vector are its I, j, and k pieces. Vector fields can be written as, say, a function m of x, y on I, and a function n of x, y on j. M and n are what you call component functions. Functions. Right, so they're both functions of x and y, and we can abbreviate this. I mean, if it's obvious what you're working in, what dimensional field you're in, you don't need to write x, y. You can just write mi plus nj, right? And these are scalar functions. So, e.g., in the previous example, m of xy was minus y, n of xy was just x, right? So these are scalar functions. These are scalar functions. They do not produce vectors. Only when they are attached to a vector does this produce a vector, right? And for a 3D field, you just have an extra p. So I mean, a 3D field is simply just mxyzi, n xyzj, p xyz k. Right, so just an extra k component on there, an extra scalar function. Okay, some notes here. One vector field that comes into play a lot down the line will be the gradient field. Recall that the gradient is a vector for any given function, right? So we can talk about that briefly. Probably even sort of, well, we can erase this. We don't need it anymore. Talk about the gradient field, in which it's no surprise. For any given point, it'll give you the gradient. So suppose we had a function f of x, y, z, and it was x squared y minus y cubed plus yz. And suppose we considered this function of 3 variables as a level surface of a 4D thing, right? So say you had this equal to 0, right? This is a level surface of a 4D guy. Then I can consider the gradient of that guy, right? So the gradient, remember, it's partial f, partial x is the I component, and partial f, partial y is the j component, partial f, partial z is the k component, right? So in this case, partial f, partial x would be just 2xy. That is the I component. And the j component is x squared minus 3y squared plus z. That's the j component. And the k component is just plus y, right? So plus y k, right? This is the gradient field. This is the gradient field for this surface, right? And this field will give you the gradient at every point that you elect to plug in there, okay? And we should remember that one of the utilities of the gradient was that at any given point the gradient gives the direction of steepest ascent. So that's the same thing here. In other words, if this is a surface, right, and at any given point you can ask what direction is the direction of steepest ascent, it will be the gradient direction, right? Okay, so that's gradient field. That's another example of a useful field. Velocity fields, gradient fields, they all come into play. Here's a silly little 3D field just to see what one looks like graphically. So here is a 3D field, very bare bones designed as just zk, right? Just zk. And we would draw a 3D field in exactly the same way we draw a 2D field, only Now we're working in 3D. So we can see here that for any point, say I plug in 1, 2, 1, the only coordinate that has any bearing on the field is the z component, or z coordinate, excuse me. So in this case, this is just k. So if I pick the point 1, 2, 1, that's 1, 2 down, and maybe you're sort of 1 up. So maybe you're, I don't know, maybe you're there or something like that. Oh, I have it here more or less. Yeah, it's about there maybe. And you're going, let's see here, am I doing what I want to do here? What I want? 1, 2, 1. Yeah, that looks reasonable, yeah. So maybe your k is like that. The hardest part of this, I think, is choosing, that's not really probably too long, is sort of choosing how to draw your points properly. So this is 1, 2, 1, right? And then if I have, what else did I have here? If I had, say, 0 or 1, 1, 0, minus 1, that's minus k. So now here's 1, and then sort of drop parallel to the z-axis. Maybe you're down there, and then you drop minus k. So this is 1, 0, minus 1. There's a couple different vectors. Again, I mean, you don't get the full effect of this the way I've drawn. You got to have some software to really get this to look really good. But it's clear, though, that here you can kind of put an easy definition on the length of any vector. The length of any vector is the absolute value of z. It's the absolute value of z, right? Because whatever z is, it's a vector parallel to the z, or the k vector. It just happens to be a different length. And what's sometimes a useful question is asking, what are all the points that map to the 0 vector for this guy? Well, the only time you map to the 0 vector is if your z-coordinate is 0, right? So if I ask, what are all the guys that map to the 0 vector, x and y are totally free. If you're in the x, y plane, though, your z-coordinate is 0, you're going to map here. So this is the xy plane. In other words, all the vectors that map to the 0 vector are the points in the xy plane. So the entire xy plane gets sent to one vector. And in fact, what's true about that is true of any point. In other words, any plane parallel to the xy plane here, every point on it will be sent to one vector. In other words, more or less this function takes, it has planes that are stacked up parallel to the z-axis, and each plane is condensed down to one point. Okay, so that's that. A couple places this comes into play in some of our calculus stuff is one place is work, and there are a couple other types of things that are similar to that, circulation, flux, and flow. We'll talk about circulation, I think, in particular. But let's get through work first. So if you recall, we talked about work a couple times. We talked about work in Calc 2. We mentioned work again early on in that dot product section long ago, when we talked about if you had a force moving in one direction and the object moving in another, work was being performed by effective force. And effective force was, or work was a dot product, right? Effective force was a vector projection. Hopefully all that rings a little bit of a bell, right? One thing is, so you remember from Calc 2, right? This definition, right? This is work done by a force f of x moving particle from A to B, right? So you had some force function, you integrate it from A to B, you get work. That's one of the things we did in Calc 2 when we had applications of integration. Well, now we're looking at not, it's still a variable force function, but now we have a force field, right? Some field of forces that's existing, like a magnetic field or a gravitational field or even a velocity field, right? Some force field. So, right? So say you have a force field, and we can talk about it in 3D as well as 2D. Doesn't really make a difference. So this is a force field in 3D. So force field in R3. Maybe it's gravitational or something. Maybe it's electrical field. I don't know. It's something, right? This guy gives a force at every point. What else do I want to say? So suppose that you're in this force field and your object is moving along a path. Say you're in a gravitational field and you're trying to fly a shuttle or something like this, right? So your field is exerting various forces on you. Your shuttle wants to take a certain path. The question is how much work is being done to move the shuttle along that path. That's what we want to answer here. So how much work to move along a smooth curve or path as t ranges from A to B, as t goes from A to B, right? So some vector position function, right? The shuttle has vector position at every point. It could certainly be a vector valued function. It doesn't need to be a function of x and y. But we can see how much work it takes to move this thing along there. Okay, so let's develop some of this a little bit. Let me draw a picture. In fact, let me make clearing here so I can get as much on one board as I can. So here is the picture. There's 3 space. And actually, I've realized earlier I was mixing up x and y. It's one of those days. But earlier when I drew points, I had x and y mixed up. So maybe if my points looked off to you, don't think it's you're not doing it right. I had the axes backwards. Nonsense. But here is your smooth curve. So say you had something that looks like this, right? So maybe there's C, right? And C exists in 3 space. Nice and smooth. And let's see here. So suppose down here, this is t equals A, and this is t equals B, right? Or I guess really I should say, to be really good, I should say this is R of A, and this is R of B. Right, so this is t equals A and t equals B on the pathway. Well, when we're trying to figure out work for the single variable case, it was an integral. So the idea was we broke up the x-axis and we looked at some partitions. Same game here. We're going to break this thing up into some subarcs. So let's chop this guy up into a bunch of subarcs of equal length. So those are equal length more or less. They're not really, but get the picture. And let's see here. So let's step 1, we'll divide C into n subarcs. And each one of them, how long is it? Well, it's delta S, right? So it's some change in arc length. Delta S is the length of each subarc. Right, that's a change in arc length, so delta S, right? And let's see here, I want to pick out one particular guy. How about this guy here? So here's the point. So maybe, I don't know how many of these there are, but say there's n of them, right? Each one, so there's n arcs. Each one has an initial point and a terminal point. So this is arc C sub I, right? So consider arc C sub I, 1 less than I less than n, going from P sub I minus 1 to P sub I, right? So if that's the 5th arc, for example, you'd be going from P4 to P5, right? So you're starting at P0 and P1, P2, P3, P4, P5, right? Okay. So at the initial point, this guy has a unit tangent vector, right? So maybe he looks like that. So that's T. And the point is that these arcs are small, right? This delta S is very small here. We're not moving very far. So if delta S is pretty small, then there's not a lot of time for this arc to change direction as away from T. In other words, we definitely know that at this point it's moving in the direction of T. Okay, it's separated here, but if that's short enough, then really, as you walk across that arc, you're more or less moving in the direction of t. It's the same idea as linear approximation. As you move away from a point on a curve, the tangent line and the curve are similar. Here, as you move across this arc, you're basically moving in the direction of t as long as the arc is short, right? So what do I want to say here? So for delta S small, move across the arc CI, you are moving in the direction of t at pi minus 1, right? So at every initial point, you have a t vector, and more or less, you're going that direction as you travel across the entire arc. Okay, now suppose that at this point, you have well, not suppose, but you do at this point have a force. You have a force field. Maybe the force is going, I have it in my picture here, it's not quite orthogonal. Maybe it's going like that, right? So maybe the force is going like that. I don't know. It's going some way. I mean, chances are it's not going the exact same direction t is going. It's going some other direction, right? So F at p sub I minus 1 is one direction, right? We're moving t at p sub I, moving in direction t. So you're moving in one direction, but your force is being exerted in another direction. Sounds like work is effective force, right? In other words, if they're going in the same direction, effective force and force are the same. Different directions, the work performed is effective force, right? So therefore, work on the ith subarc is effective force. Effective force in the direction of t. In other words, you want to go t direction, the force is pushing off in some other direction. Effective force in the direction of t is what's creating the work. All right, am I out of space here? Sort of. So if you recall, this effective force was a vector projection, right? It was a projection of F onto t. So maybe you had something like, so you had t that was going like, the line through t was like that, and we dropped that perpendicular, right? And there was your vector projection. That rings a bell, hopefully, right? So come over here. For the subarc C sub I, right, the work is approximately, well, it's the vector projection. My notation here is necessarily clunky, but don't get too caught up in it. It's the projection of F at p sub I minus 1 onto t at p sub I minus 1. So it is this times delta S. In other words, this is effective force. This is the distance that you're moving. So this projection vector's length is the effective force, right? This is how far it's traveling across the arc delta S, right? So the work is approximately that. And I say approximately because we're not always traveling in the direction of t. We're approximately going the direction of t most of the way, right? Okay, so what is this? If you remember back to projections, we defined projections in terms of dot products. In particular, it was this dot product. It was t dot f over length of t. And this is all at the p sub I minus 1 times delta S, right? So this was what we defined it to be, right? And that was, and the good thing here is that this is a unit vector. Its length is 1, so this winds up being t p sub I minus 1 dot f p sub I minus 1 times delta S, which is the length. All right? So we have that. So this is an approximation for the work done to get across one of the n subarcs. All right. How do integrals work? Well, we have an approximation for one chunk. All the chunks follow suit. Add up all these guys over all the subarcs as the delta S term goes to 0. Right? So add up estimates for all arcs, pass to a limit as delta S goes to 0, right? So there's that. What do you get? You get a definition of work, which is somewhat similar to what we had before. So this is now integral from t equals a to t equals b, f dot t ds, right? So f dot t dot f down there doesn't make a difference which one goes first. It's commutative. So this is our initial work integral. Now the problem is we don't like having this ds. It was a problem in the last section on line integrals. Well, we don't like to have it here either. So we're going to use the same kind of tricks we used last section to get rid of it. So recall a couple things. First of all, unit tangent is derivative over length of derivative, right? So it looks like that, right? We also had the notion that ds was length of r prime dt. That was from last section too, right? So this could be replaced with something in terms of t, which is good because now we have things that are entirely in terms of t here, right? Well, almost. This is still an xyz guy, but that's all right. So let's take our initial thing. Let me just go ahead and write down here. So this is now t from a to b. This is f dot r prime of t over length of r prime of t times length of r prime of t dt, right? So this is literally what I get when I sub in these two. Cancel, cancel, right? Everything in terms of t now. This is an x, y, z, but x, y, and z are a function of t. This is r of t, right? So this is now a to b f dot r prime of t dt. And oftentimes as a shorthand, what you see here is you see the following. And this is how many books refer to it. This is just f dot dr, right? This dr down here, a shorthand for dot the derivative with respect to t. So this is often the shorthand. This, however, is the nitty-gritty thing to keep in mind here. Okay. This is a function of x, y, and z, right? Along the pathway r of t, x, y, and z are functions of t. So this entire thing is a function of t, right? This is a line integral with respect to t. So this guy is a line integral with respect to t. All right. So let me say that up here briefly. If you have a vector field f, if you have a continuous f defined on smooth curve c equals rt, right? Then we can define the line integral of f along c is t equals a to t equals b. It's that, and it's the shorthand f dot dr, right? And really, probably in its most useful form, it is f at r of t times r prime dt. So it's this last one that is friendliest to calculate with. This guy over here helped motivate the geometry, certainly. This guy here is a nice compact shorthand for it. This guy here is what you're going to want to use when you're actually computing these line integrals and these works. And it turns out that we're going to see that there are several other equivalent definitions of this integral that aren't work, but there's something similar to it depending on the field. A force field generates work. For example, a fluid flow field generates circulation and flow, so you get other things like that. Okay, let's try an example here. It's a lot of abstraction at once. So let's see here. We can try to find some work over a field. So let's give us a field first, f of x, y, x squared I. Oopsies, I wanted minus, didn't I? Minus xyj. There's your force field. That's a force field. Okay, suppose we have a particle moving along the following path. This is a quarter circle, so say cosine ti plus sine tj, right? And we'll cut it to be the first quadrant. So 0, pi, or to pi over 2, yeah. So in other words, my question is, how much work is done moving a particle along this path through this force field? How much work is done moving a particle along this path through this force field? All right, first thing to do, get f in terms of t, minus xyj, right? F of r of t, right? We plug in x squared. This is the cosine squared ti. Let's say this is minus cosine t sine tj, right? This is, let's see, I'll do with it? Nope, that's it. That's as simple as it gets. This is f of r of t, right? This is the path along the vector field. In other words, this is where the path and the vector field intersect, path into the vector field. Okay, r prime, where's r? Up here. So r prime is a minus sine ti plus cosine tj, right? Work then is integral 0 pi over 2. Let's see, the shorthand is f dot dr. Slightly longer hand, f of r of t dot r prime. Let's see here. So if we dot these guys together, what in the world do we get? We get negative cosine squared sine minus cosine squared sine again, right? So we really get integral 0 to pi over 2 minus 2 cosine squared t sine t dt, right? Is that what I have? Good. Okay. Substitution, straightforward here. Let u be cosine, du is minus sine t dt, right? So that takes care of everything down here. There's our minus 2 sine. We get u squared, so we have 1/3 u cubed coming out of this thing. All right, so we wind up with, and we don't need the negatives over here, right? So, yeah, so we can just do this. We can rip out this minus 2, and this guy is 0 to pi over 2, so it's it is 0, or it's well, I'm not going to bother writing all the u's down, but you do end up with, what do you end up with eventually? 2 times 1/3 cosine cubed t. Do I believe that's true? Right? You have to go ahead and switch it around, because if you plugged in 0 to pi over 2 for the u's, you go from 1 to 0. You have to reverse the order of that. So that's not a bad thing, but still it's good to practice that and check and make sure you know what you're doing. So plug this in, and you do wind up, and what happened to my, oh, I see, yes, okay, that's okay, yeah. So this is minus 2/3 joules. Yeah, it's minus 2/3 joules. And I didn't give units up here, but we can say joules. I'm assuming units of force are in newtons, and units of distance are in meters. Right? So Force is in newtons, and this is in meters, this is in joules, right? So the work is negative, right? So that may seem to be wrong. It may cause you to question it, but let's take a look and see what is going on here. Let me put the same picture over here. So here's a picture. Here is the quarter circle, and we're traveling counterclockwise, right? Because we're moving from 0 to pi over 2, right? It turns out if you graph some of these force vectors, the force vectors look something like this. And you can check this out. They're kind of pointing like in that direction. So maybe I have a better idea. Let me make this really stand out. Let's highlight this. Here, we'll put this in red. Here's the quarter circle. You're going like that along the quarter circle. The force field is going like that, right? So the field is opposing the movement of the particle, right? So field is actually opposing the movement of the particle, right? The orientation of the curve is against the movement of the field, right? So in a sense, it's like you're swimming upstream, essentially. You're swimming against the current, right? The current's going like this. You're trying to move like this. The current's working against you. It's opposing you. If we actually switch these guys around, right, if we now had the orientation switched from pi over 2 to 0, right, so now we are moving along this curve clockwise, and now we're going with the flow of the field, exactly the same measurement magnitude-wise would come out, but it would be positive. So if we switched the orientation of the curve, now we start at 0, 0, 1 and go to 1, 0, then this becomes positive 2/3 joules. Okay. So there's work. All right, one other thing to talk about here is circulation. It turns out circulation is actually computationally equivalent. The same line integral will get it for you, but just happens to be a slightly different physical interpretation. I think it's still worth mentioning. So say you're not in a force field now. Say F is a velocity field. In other words, we talked about at the beginning of the lecture, a pipe and a fluid moving through it. Right, so this is a velocity field. Let's suppose we have a curve here, but a special kind, closed. That is to say, its beginning and ending points are the same. So this is closed curve, closed curve. That is to say, its beginning and ending points are the same. So for example, a circle is a closed curve, and a line is not. So they don't end the same place. A circle does, though, right? This integral, right, so remember, we had this notation for around a curve, right? This line integral notation. Right? This is f dot t ds. This is a circulation of f around c, right? So circulation of f around c, right? What do I want to say here now? Yeah, so let's talk about this a minute. The projection vector played a role in the work computation, right? Remember, it was f back down to t. Well, do you recall that the scalar component of that, the component in the direction of t, was the length of the projection vector, or the negative of its length if it went in the opposite direction. So this is a scalar. This is just f dot t over length of t, and we know that's just f dot t since t is a unit, right? So f is a velocity in this case. This is, so I call it in the notes, it's an effective velocity in the direction of t. In other words, if you're moving at a certain velocity, right, this is a measure of how much of that velocity is actually going in the direction of t, right? So in other words, velocity is trying to take you somewhere. In other words, the fluid wants to do something like this. If you sort of force it to go some other direction, you're sort of fighting against effective velocity. But this is a measure of how much velocity is going in this direction. in the sense that if I walk straight forward across the board here, right, all my motion is traveling in this direction here, right? But if I walked up a set of stairs here, maybe I walked up like at a 45-degree angle, right? Then I'm going in this direction towards the ceiling, but I'm also still partially moving here, right? In other words, I'm still moving forward, but not entirely forward. Now I'm going up and also forward at the same time, right? But there's still some velocity carrying me in this direction. That's the idea of effective velocity. Same idea as effective force, really. And so let's talk about this for a minute here. What is this thing? Remember, one way to talk about it was the length of f times the length of t times cosine theta, the angle between f and t. Remember that definition from dot product? This is maximized, and theta was between 0 and pi. This is maximized when theta is equal to 0, right? In other words, this is 1. This is the most maximum here. That is to say, if theta is 0, there's nothing, in other words, f and t are pointing in the same direction. F and t point in the same direction. Makes sense. If f and t are going in the same direction, then the velocity and your movement are traveling in the same direction. All the velocity is going one direction. All the effective velocity is going one direction, right? So I don't want to erase this yet. As a consequence, this line integral, right? The line integral, which is a number of different definitions, this is one of them. This was the geometry we talked about just a minute ago, right? This thing, right, this integral of this thing is maximized for a given curve, at least, when f and t point in the same direction at every point on C. At every point on C. So imagine if I am, say my velocity field is circular. It's a whirlpool field, right? But it's not moving inward. It's just a steady stasis of whirlpool, right? In other words, it goes around and around, right? If I am walking always in that circular path anyway, right, my movement and the velocity field are always the same. In other words, I'm always pointing the way the velocity field wants me to point, right? This integral is going to be maximized. So this is circulation. In this sense, circulation is a measure of tendency to circulate around a curve. In other words, if it's maximized, the fluid is totally circulating. In other words, if this is at a maximum, the fluid is entirely moving the way of the velocity field. It's not doing anything else, right? If it's not maximized, there's some places where the fluid wants to follow a path different than what the velocity field tells it to follow. Just like the example of, say, a swimmer. If I jump into a stream with a current and I sit there, I allow the stream to carry me, my pathway and the stream's velocity field are the same. I'm always moving the way the stream wants me to move. But if I swim, any wave is against the current, I'm trying to move in a way different than the velocity field. In other words, my movement, my direction is going to be different than what the field wants me to do, right? I'm not going to be following the same way. And circulation is just a matter of a closed curve. So closed or open doesn't matter so much. It's just a matter of the terminology. But if for example, I was swimming in a whirlpool, if I'm always swimming with the whirlpool, I'm circling around and around, I'm going the way the whirlpool wants me to go. If I try to break out of the whirlpool and go some other direction, I no longer am maximizing this, right? So what about other things that can happen? Well, what if f and t is 0, right? Then what you have is orthogonality. F and t are orthogonal, right? That is to say, if f and t are always orthogonal, the fluid won't circulate at all. If you're trying to move So in other words, think back to the example of me walking. I walk this direction, I follow the path of velocity. If I walk up the stairs, I'm going a different direction, but I'm still moving somewhat this way. If this is the flat ground, if I go orthogonally to it, heading right towards the ceiling, right? I'm heading straight up. I'm not walking at all in this direction, right? I have no ability to move in this direction whatsoever. There's no effective velocity going that way. It's all pointing towards the ceiling. I'm not moving anywhere to the right, right? If these points are orthogonal, or if these vectors are orthogonal, the fluid won't circulate at all. There's going to be no circulation around the field at that point, okay? And if they're maximized in the negative direction, that is to say, this angle is pi, right? So cosine of theta, or cosine of pi is the -1. This is going to be a -1. They'll point in opposite directions. So here, F, or I don't want to say this here, F and T, I should say here actually, F and T are orthogonal. Fluid will not circulate, right? And F dot T -1, fluid and field are in opposite directions. That is to say, in the whirlpool example, I'm still entirely caught in the path of the whirlpool, only now I'm swimming backwards against its flow, right? So I'm not getting out of its pathway at all. It's going around in a circle. I'm going around in a circle, only it's going, say, counterclockwise. I'm going clockwise around it. So that's not a real good idea from, a whirlpool. That doesn't help me. But still. Okay, so circulation is a measure of a tendency of a fluid to circulate around a closed curve. All right, let's try an example here and see if we can't get some concreteness of some of this discussion. Okay, let me get rid of everything up here. So we'll see that the calculation-wise, this is the same thing we just did, essentially. Let's give a field. Here's the field we started with the lecture. This was that field, negative yi plus xj, that guy that had sort of like a widening whirlpool field. It was a very tight circle near the origin, wider circular berths around the outside, right? Not really, well, sort of circular. And let's say, so this is a velocity field. Okay, the closed path along the path, let's make it two pieces. The first piece will be a semicircular arch. We'll call it cosine Ti plus sine Tj. And let's have it working from 0 to pi, right? So you're along this, so your pathway initially looks like this. So there's the x-axis. So you're going, so there's R1. That's a semicircular arch, right? Okay. And then let's do a line segment. Just Ti from -1 to 1, right? So now you're going, so here you are at -1. Now you're going just like that. So there is your pathway, right? And so if we call, so this is R2 down here, right? And remember that line integrals have finite additivity, so I could simply take the integral over the arch plus integral over the line segment, I get the full integral, right? That's not a problem at all. So if I call this whole thing C, then if I do the integral along C, then it's just the integral of each piece separately. So call this C1, call this C2, right? I mean, that's what we had from last section. Okay, we need a couple different things here. We need f of R1 of t. Where's R1? There it is. So we need minus sine Ti plus cosine Tj. and we need f of r2 of t. Where's r2? Here it is. So that is my x. So that's just tj. Right. And how about the derivatives? R prime is minus sine ti plus cosine tj, and r prime of 2 is just I. So derivative of all those points in one direction. Makes sense. The line has constant tangent vector. So do I have room to do this down here? I think so. This line integral is in two pieces. First piece is 0 to pi. Dot product here, sine squared plus cosine squared. Sine squared plus cosine squared t dt. We know that's just 1. Second, negative 1 to 1. Here, it's interesting. What happens, the dot product is 0. So this is actually 0 dt. This actually adds nothing. This actually adds nothing except possibly an initial value or something like that. We don't have that here. But so this winds up being integral from 0 to pi of 1 dt, which is just pi, right? And take a look. This piece didn't add anything at all. And let me draw some vectors on the vector field. Remember, vector field, let me try to draw it without being quite so point-wise precise so it looks better. The vector field was sort of a circular pathways, right? So well, I'm going to have to redraw this. We can do that, though, can't we? So let me redraw over here. There is a semicircular arch. Here's the path. Bam, 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 bam. All right. Now, how does the force field look? The force field rotates sort of like this. So it's in sort of these ever-widening circular patterns. And I'm trying to draw these tangentially to the semicircle. I don't know how well that's coming off, but so there's sort of like this inner circle. Here's this outer circle. And there's an even bigger outer circle out here. Doom, doom. These aren't, I'm not being very precise here, but you can check this out and you'll see that you do in fact get these rings, right? Take a look here. There's no circulation along the line segment. It doesn't add anything at all. It's got 0 here. So for points along the x-axis, right, for points that are x, 0, the forces are all going to be xj. So the forces here are all pointing, well, actually, those are negative, but they're all pointing down a little less, little less, little less, little doo-doo, doo-doo, doo-doo. But do we see these arrows along the x-axis are completely orthogonal to the path of motion, right? No circulation at all, right? Fluid in this field is not going to move along this path if it follows the field. In other words, it has no tendency at all to follow this path in this field, right? Whereas along the arch, they match perfectly. The velocity vectors are the field vectors. Take a look. I mean, negative yi is negative sine. Xj is cosine. They match entirely, right? These vectors are the field vectors. The circulation is maximized along the arch, right? Circulation is maximized along the arch. What else do I want to say here? Okay, yeah, we can say this too. So if you look at this is literally it's ft cosine theta. right? T is 1, so this is really just length f cosine theta. Along the arch, this is always 1, right? So this is actually just equal to length of f along the arch, right? And so this is always equal. This is always equal to the length of f if this is maximized. So along this arch, these force vectors, they all have a length of 1, right? If you take cosine squared plus sine squared, and you put negatives in there, it doesn't matter, you get a length of 1, right? So this length of f is 1 everywhere on the arch, everywhere on R1 of t, right? Do we see in the sense that the force vectors here along this arch, where is it? Are these vectors, their length is always 1. So in that case, if I took just this line integral, right, part of this adds nothing. This part is just the integral of 1, right? So this is, in fact, the arc length of R1 of t in this case, right? Because this is integrating the function 1 there, right? That gives you arc length in this case, which is an interesting little observation. Units is in order here, I guess. I'll talk about units in a minute or a second. Units are kind of funky sometimes. So maybe the velocity is in meters per second. Maybe this pathway is in meters. So the circulation units are meters squared per second, right? So it's f dot dr, right? So it's meters squared per second. It's meters squared per second squared, and when you integrate, you go back to meters squared per second. So the units are sort of a little bit fuzzy. And also, if this is not a closed curve, I said this earlier, you call this just a flow integral. So circulation and flow are the same thing. Circulation applies to something that's closed. Flow can apply to, say, going down a stream. Okay, that's it.